true shape of the section is an important element in the projection of cut solids. It is significant when you consider the cross-section of irregular solids especially, or to get the complete details, internal details of a solid. Now let us see the techniques of or the basic principles of projection of true shape of the section. Here you have, it's an example, here you have a square pyramid cut by a section plane, and this section plane is perpendicular to VP and inclined to HP. Say the solid is resting on HP. Okay, so you have PQRS as the section. Now, when you consider its projection, the projection of the solids, the projection of the solid under section, when you consider it, see, we have the trace in the elevation. Okay, so PQRS is the plan of the section, and PQRS is obviously not of its true shape or size, because the line features of this surface, this plane, is not parallel to the plane of projection, I mean HP, because PQRS is projected on HP. It is very clear. You consider Q dash R dash and QR, both are inclined to the XY line, so QR is not showing its true length in this plan. Similarly, PS not showing the true length in this plan. Therefore, PQRS is apparently of not having its true size or shape. Now our task is to get the true size or true shape of the section, and we just consider ABCD. This ABCD, it is a plan of the bottom surface of the solid. ABCD shows its true size. How? Because BC, when you consider BC, B dash C dash BC, both are parallel to the XY line. Similarly AD, and here AB is perpendicular to the XY line. It is converged to a point in the elevation. Therefore, the line features of this ABCD, they show the true length. Okay, hence we can say that ABCD of its true shape. How do we get this true shape for ABCD in plan? Because the bottom surface is projected to the horizontal plane on which it is resting. In other words, ABCD, the surface, bottom surface ABCD is parallel to HP, and it is projected on HP. Obviously, you get the true shape. Had this PQRS cut surface been projected to a plane to which it is parallel, we would have got its true size. That is the principle of projection of true shape. Okay. Now the question is, how can we employ a plane of projection to get the true shape for this cut surface? The immediate answer is the cutting plane itself. Okay. If the cutting plane is used as a plane of projection, we will get PQRS on it as a projection with its true size and shape. Why? Because PQRS is parallel to it, because PQRS is very much lying on it. Therefore, if we project PQRS on this cutting plane, we will get the true shape for the cut surface. So that now this principle leads us to have a new systems of projections, planes of projections. Okay, so we have the BP and HP are principal planes of projection, and apart from that we can have an additional plane for projection. Okay, which is the cutting plane, and here according to the given conditions this cutting plane is perpendicular to VP but inclined to HP. Okay, so here we have VP, HP or principal planes of projection, and this cutting plane will act as an auxiliary plane of projection. Okay, an auxiliary plane of projection, right, which can serve as a plane of projection to facilitate the true shape for the section. Okay, since it is perpendicular to VP like our conventional HP, it can be considered as an auxiliary horizontal plane. Okay, AHP. That name for auxiliary horizontal plane, that name implies that we can make use of this plane to project an auxiliary plan over it. Okay, we have PQR as a plan projected on the original horizontal plane, which does not show the true shape. So we have another plane, an auxiliary plane, on which we can project the same plan, but it will show its true shape there. Okay, now according to our conventions, when you can rotate the planes of projections to get a two-dimensional plane altogether. Okay, so we'll have VP above, right, HP here, and here you will have the cutting plane. Okay, so above this portion will be the cutting plane area, which can be used as an auxiliary horizontal plane. And here you have the VP area, here you have the HP area. This is your principal reference plane, reference line XY. So it can be considered as X1, Y1. Okay, an auxiliary reference line. Okay, so the same, this can be incorporated here. But when you use this area as the plane of as the plane of projection, the projection may get messed up with your original elevation. So we can consider a plane which is parallel to this cutting plane. Instead of taking this cutting plane as such, you can consider another plane which is parallel to it, which is parallel to this cutting plane as our auxiliary horizontal plane. Okay, so then you can have the auxiliary reference line X1, Y1 at a convenient distance from this cutting plane. Okay, now the question is only to project, say, the point P over this, on this horizontal, auxiliary horizontal plane. Okay, the question is only, now the question is how to project the point of the point P on this auxiliary plane of projection. Remember, this auxiliary plane of projection is perpendicular to VP. Okay, perpendicular to VP. That means this line represents the trace of that auxiliary plane of projection on VP. Okay, see, this is our plane. The points P, Q, R, S, okay, the corners of the cut surface, all are on this plane, and you are rotating this plane. Okay, you are rotating this auxiliary horizontal plane to make it coplanar with VP. Okay, so that is why we have a construction like this here. Now the question is how to plot the projection. Okay, so for that you are extending a projector from that point, okay, point of intersection of the edge OA with the cutting plane, that is P. You are extending a projector. Okay. Now we need this distance. Okay. And that distance will be same as that of this one, isn't it? The distance of P measured perpendicular to the vertical plane. Okay. Distance of P measured perpendicular to the vertical plane is nothing but the planned distance of P, isn't it? The planned distance of P. Okay. So this is the P, the plan of P. Plan of P means the distance of P from vertical plane. Okay. Here also we are concerned about the distance of P from the vertical plane. So here on this projector, from this reference line, you mark a distance which is equal to distance of P from vertical plane. That is nothing but planned distance of P. Okay. So here that will make you the P, the point P, which is nothing but the projection of the cut surface, which represents the true section. Since it represents the true shape, I mean since these points represents, since the point P represents the corner of a true section, it is the projection is represented by a capital letter. So Q, R and S. Okay, Q, R and S you can plot by considering the planned distances of Q, R and S. So on joining you will get a polygon which represents the true section. Okay. Now here we have to note one point, that here the cutting plane is perpendicular to VP. Okay, cutting plane is perpendicular to VP. I mean, so it is represented by a trace in the elevation. We get the true section by considering the planned distances of the points of intersection of the cutting plane with the edges. So we can say that if the cutting plane is perpendicular to VP, we get the true section as an auxiliary plane. Okay. With the same logic, we can say that if the cutting plane is perpendicular to HP, then the trace will be here in the plan, with the plan. In that case, the true section will be obtained as an auxiliary elevation. You will take the measurements, you will take the distances of the projections as the distances of the points from horizontal plane. That is the elevation distances. You will take elevation distances. Therefore, you will get the true section as an auxiliary elevation. Okay, it will be more clear when we consider certain examples.